There's a moment just after sunset when the first stars begin to pierce through the fading blue. You might look up and see them scattered across the sky, small points of light, all appearing roughly the same size, gentle and distant. We've learned not to trust that impression. We know now that what looks like a pinprick could be a sun many times larger than our own. But even knowing this, it's difficult to prepare the mind for what exists out there. Somewhere in the darkness, separated from us by thousands of light years, there burns a star so enormous that if you placed it where our sun sits now, its surface would reach beyond the orbit of Saturn. Everything we know, Earth, Mars, Jupiter, would be inside it, not orbiting it, inside it. How do we hold an idea like that? How does the universe permit something so vast to exist when the stars above us seem so uniform, so restrained? And what does it mean that we, standing on a small world circling an average star, have found it? For most of human history, stars were lights. They were fires in the sky, holes in a celestial dome, the eyes of gods watching from above. No one knew how far away they were. No one knew they were suns. The brightest stars were assumed to be the most important, Sirius, Vega, Arcturus, because brightness suggested power, closeness, divine favor. Size was not a question anyone thought to ask. The stars were eternal, unchanging, and beyond reach. Even as astronomy became a science, stars remained mysterious. Telescopes revealed mountains on the moon and moons around Jupiter, but the stars themselves stayed as points of light. They were too far away to show a disk, too distant to measure directly. It wasn't until the 19th century that we began to understand what they were made of, how they shone, why they differed in color. And only in the 20th century did we begin to grasp their true variety, their births, their deaths, their staggering differences in mass and scale. By the mid-1900s, astronomers had catalogued thousands of stars and noticed patterns. Some were small and dense. Some were dim and cool. Others were bright and hot, burning through their fuel in mere millions of years. And a few, just a few, were unimaginably large. These were the supergiants and hypergiants, stars at the extreme edge of what seemed physically possible. But even among these titans, one stood apart. In 1860, German astronomers at the Bonn Observatory were mapping the southern skies when they recorded a faint star in the constellation Scutum. They catalogued it, assigned it a number, and moved on. For over a century, it remained just another entry in a growing list of celestial objects. It wasn't particularly bright. It wasn't easy to observe. It existed in relative obscurity until the 1970s, when advances in infrared astronomy allowed us to see it clearly for the first time. What they found was astonishing. The star, later named UY Scuti, was not faint because it was small. It was faint because it was dying, shrouded in layers of gas and dust it had shed over millennia. When astronomers corrected for this dimming and measured its true luminosity, they realized they were looking at something extraordinary. UY Scuti was a red hypergiant, a star in the final, unstable stages of its life, and it was radiating with the power of hundreds of thousands of suns. But it was the physical size that defied comprehension. Using a method called interferometry, which combines light from multiple telescopes to simulate a much larger instrument, astronomers measured the angular size of UY Scuti as seen from Earth. Then, knowing its distance, roughly 9,000 light-years, they calculated its radius. The numbers were almost absurd. If you could somehow transport UY Scuti to the center of our solar system, its outer layers would extend past Jupiter, possibly even as far as Saturn. The Earth would be a speck of dust deep within the star's glowing atmosphere, vaporized long before it could complete a single orbit. To say it is large feels inadequate. It is so large that light, traveling at 300,000 kilometers per second, would take nearly 7 hours to cross from one side to the other. You could fit more than 5 billion suns the size of ours inside its volume. But stars like UY Scuti are not stable. They are not meant to last. In fact, their size is evidence of their impending end. When a star is born, it begins as a collapsing cloud of hydrogen gas. Gravity pulls the material inward until the core becomes dense and hot enough for nuclear fusion to ignite. For most of a star's life, this fusion of hydrogen into helium provides an outward pressure that balances the inward pull of gravity. The star settles into equilibrium. Our Sun has been in this state for nearly 5 billion years and will remain so for 5 billion more. But massive stars, stars born with many times the mass of the Sun, burn through their fuel far more quickly. The core runs hotter, fusion happens faster, and within just a few million years, the hydrogen is exhausted. When this happens, the core contracts and heats up further, igniting helium, then carbon, then oxygen. Each new fuel burns faster than the last, and with each stage, the outer layers of the star expand. The star swells into a supergiant, then a hypergiant. It becomes enormous, but fragile. UY Scuti is in this phase now. Its core is likely fusing heavier and heavier elements, while its outer envelope has bloated to a size that defies the usual rules of stellar structure. The surface gravity is so weak that material constantly drifts away into space, forming a vast shell of gas around the star. It pulses. It fluctuates in brightness. It is unstable in ways we are still working to understand. And soon, perhaps in tens of thousands of years, perhaps tomorrow, it will explode. When a hypergiant dies, it does not fade quietly. It detonates in a supernova, one of the most energetic events in the universe. For a brief moment, a single dying star can outshine an entire galaxy. The core collapses into a neutron star or a black hole, and the outer layers are flung into space at tens of thousands of kilometers per second. Elements forged in the star's core, carbon, oxygen, iron, gold, are scattered across light years, seeding the universe with the raw material for new stars, new planets, perhaps new life. UY Scuti will end this way. When it does, we will not see it happen in real time. The light from the explosion will travel for 9,000 years before reaching Earth. By the time it arrives, human civilization may look entirely different. We may no longer be here at all. But the light will come, and if anyone is watching the sky, they will see a new star appear where none was visible before. It will burn brightly for weeks, then fade, leaving only a remnant, a ghost of something that was once the largest star we had ever found. But UY Scuti may not hold that title forever. Our measurements of stellar size are uncertain. dependent on distance estimates and models of stellar atmospheres that are still being refined. Other candidates exist. Stephenson 218, located in a massive star cluster over 20,000 light-years away, may be even larger. Some estimates place its radius beyond that of UY Scuti, though the uncertainty is significant. There are others. WOHG 64, VY Canis Majoris, Westerlund 126, all hypergiants, all nearing the end, all contenders for the title of largest known star. What is clear is that there exists an upper limit. A star cannot grow indefinitely. At a certain point, the radiation pressure from the core becomes so intense that it begins to blow the outer layers away faster than gravity can hold them. The star loses mass. It destabilizes. It begins to tear itself apart even before the final explosion. This is the Eddington limit, a boundary set by the physics of light and gravity, and it suggests that stars like UY Scuti are near the maximum size the universe allows. We are witnessing something rare. These hypergiants are short-lived, unstable, and few in number. In a galaxy of hundreds of billions of stars, only a handful reach this scale. To find one, to measure it, to know it exists, is to glimpse an extreme edge of stellar evolution, a place where the usual rules bend and the forces of nature struggle to maintain balance. And yet, for all its size, UY Scuti is not the most massive star. Mass and size are not the same. A hypergiant is enormous because it has swollen in old age, not because it contains the most matter. There are smaller stars, blue hypergiants, Wolf-Rayet stars, that pack far more mass into a smaller volume. These stars burn hotter, shine brighter, and die even faster. UY Scuti is vast, but diffuse. Its outer layers are barely denser than the vacuum of space. If you could somehow stand on a platform at its surface, you would see a faint glow around you, but you would not feel solid ground beneath your feet. There is no surface in the way we understand it. Just a gradual thickening of gas as you move inward toward the core. This is what scale does. It makes familiar concepts strange. A star is no longer a sphere of fire, but a tenuous envelope of plasma held together by gravity, radiating energy across billions of kilometers, slowly unraveling as it nears its end. We do not see UY Scuti with the naked eye. We never have. It is too far, too dim, too obscured by dust. Even with telescopes, it appears as little more than a reddish point, unremarkable among the thousands of other stars in that region of the sky. But we have measured it. We have modeled it. We have used mathematics and physics to reconstruct what it would look like if we could approach it, orbit it, witness it up close. Imagine that journey. You leave Earth and travel outward through the solar system, past the rocky planets, past the gas giants, into the cold expanse beyond Neptune. You continue for years, decades, lifetimes, accelerating toward the speed of light. You cross light years of empty space, through regions where stars are separated by distances so great that their light takes years to travel between them. And then, slowly, a red glow appears ahead. At first, it is faint, just a dim ember in the blackness. But as you draw closer, it grows, and grows, and grows. By the time you are within a few billion kilometers, the star fills half the sky. It is not a point anymore. It is a wall of light, a horizon of glowing gas stretching across your field of view. You are still farther from it than Earth is from the Sun, but already it dominates everything. You continue inward. The light intensifies. The heat builds. And you realize with a strange kind of awe that you are not approaching a star. You are entering one. There is something humbling in this. We are accustomed to thinking of Earth as our reference point, the scale against which we measure everything else. But standing beside UY Scuti, Earth would be invisible. The Sun would be invisible. All the planets, all the space we have ever explored, would fit comfortably inside the outer envelope of a single dying star. And this is just one star. One object among billions in our galaxy, among trillions in the observable universe. There may be larger stars we have not yet found, hidden in distant galaxies, burning in regions of space we cannot yet observe. Or perhaps UY Scuti and its kin represent a true maximum, the largest structures gravity and fusion can sustain before they collapse under their own instability. Either way, we are left with a quiet realization. The universe is not built to our scale. It is not interested in what we find comprehensible. It simply is. And yet, we continue to measure. We continue to search. We have sent spacecraft to the edges of the solar system, pointed telescopes at the farthest galaxies, analyzed light that has traveled for billions of years to reach us. We have discovered worlds unlike our own, stars unlike our sun, phenomena that challenge everything we thought we understood. And in doing so, we have learned something unexpected. The universe, for all its indifference, is knowable, not entirely, not perfectly, but knowable. UY Scuti will die. Its light will fade. The gas it has shed will drift through space, mixing with the interstellar medium, eventually collapsing to form new stars. Some of those stars may have planets. Some of those planets may have life. And if that life ever looks up at the sky and wonders what else is out there, they will be asking the same question we are. There are nights when the sky is clear and the stars seem impossibly distant. We know they are suns, we know they are vast, but the knowledge sits quietly in the background, abstract and untouchable. Then occasionally something shifts. You read a number, you see an image. You let the scale of it settle in your mind, and for a moment the distance collapses. You are standing on a small planet, circling an average star, looking out at a universe filled with objects so large, so far, so indifferent to your existence that it should feel crushing. But it doesn't. It feels like discovery. UY Scuti is out there now, glowing faintly in the constellation Scutum, unaware that we have measured it, named it, called it the largest. It will burn for a while longer, shedding light across the void, until the moment when its core can no longer sustain itself. And then it will end, violently, brilliantly, briefly, but the light will travel. It always does. And someday, thousands of years from now, someone may look up and see a new star appear in the sky. They will not know what it is. They will not know how far it has come, but they will see it, and they will wonder.